Good day and welcome to today's class. So today we want to look at another types of number systems called the rational numbers. Okay, but before we talk about the rational numbers, let's quickly look at the previous number we discussed. Okay, because this rational number will be generated from that number. Okay, so you will recall that in our last class we discussed the types of number called the integer numbers, okay, whose elements are elements from the negative largest integer, okay, up to -2, -1, 0, then to positive integers up to the largest uh, positive integers. Okay, so you recall that we have said that this number are divided into three parts. The first part being the negative integers, the integers, the zero integer, then the positive integers. Okay, so we have also looked at some of the properties of these numbers, and then in conclusion, we said this number is not a field because it's faced in one of the axioms of field. Okay, and in our previous class. Okay, so also something we should also note here is that this number contains uh, another two kinds of numbers. These are odd and even numbers. Okay, as you can see, both numbers alternate in this set. Okay, the negative number 3 here, the negative 3 here is an odd number. This is even, odd, even, odd, even, and so on. Okay, so but that is not where we are going. Okay, we actually want to discuss another kinds of number which contains these numbers, and this number, as we have said earlier, is called the rational numbers. These rational numbers are has a symbol Q, but this Q is represented in the glyph form. Okay, and it is defined. This Q is defined as a set is given as a set A divided by N, such that this A, which is the numerator here, is an integer number, while the denominator N is a natural number. Okay, so any forms of a number we can get from this point, okay, the set of elements there are all referred to as the rational numbers. Okay, this definition has actually been refined from the one defined by the earliest mathematicians. Okay, what the early mathematician did is that they have defined this set as the quotient of two integer numbers. Okay, by choosing the denominator not to be 0. Okay, but if Q is not equal to 0, that is the denominator is not 0, okay, we will see that it means it will have some of the positive and negative numbers. Okay, so if it is positive, that is quite okay because it's conform with what we have here. But if it is negative, okay, you will see that this sign here will be affecting that of the numerator. And if we are to define this q here as earlier we defined, okay, this set of numbers we will exhibit a lot of redundancy, okay, of rational numbers of the same kinds, okay. So in order to do away with, though the set will be the same, but okay, in order to reduce some of the repetitions in the set, okay, this is more appropriate, okay, this is more appropriate, okay. And then in order to see some of the elements in the set, let us, okay, describe a table, okay, just to show some of the few elements of the set, okay. So on this table, I want to consider the operation here, this operation as it is here, okay, where the elements, the integer numbers are the elements here, while the natural numbers are the elements here, okay, just few, okay. And then let's say from -4, -3, -2, -1, 0, 1, 2, 3, 4. Then this goes to infinity. So if we perform the operation as we have it here, okay, we'll see that this first of element will repeat because everything here are divided by 1, okay. Okay, so as we can see, all what is here is the integer numbers z, as we can see, okay. And this type of rational numbers are referred to as the embedded integers, okay. So we'll talk more about that on the when we are talking about some of the features of these numbers, okay. So then if you perform the second line here, so this will be -2, okay, also an integer, okay. The next one is -3/2, -1, -1/2, 0, 1/2, 1, okay, 3/2, then 2, okay. Then also this continues, okay. We also have -2/3, -1, -2/3. Oh, this is a -4/3, sorry, okay. So this is -1/3, 0, this is 1/3, 2/3, then 1, then 4/3. This also continues, okay. Again, we have -1 here, and -3/4, -1/2, -1/4, 0, 1/4, okay, 1/2, then 3/4, 3/4, then 1, okay. So these are some of the few elements in this set, as we can see, okay. So looking at this table, okay, in order to group this in another form, that some of the number, each type of number form a pattern here, okay. Let's say, for example, the number 0 can only be seen with this pattern, okay, down. Anywhere you see 0, okay, locate it at the middle here, okay. As we can see here too, the number 1 will also have this pattern throughout, okay. Also, we can see another number here, -1, which also has this pattern throughout, okay. There are some of the numbers too, like 2, okay. This will be skipping a number here then. So the next number we'll see for 2 will be a number here, then another 2 should exist somewhere here, okay. That's the case when we have 3 here, then, okay. So another number should be coming here. That's when 3 is divided by, when 6 is divided by this, by 3. So somewhere we have to, of course, a number will come here before this, okay. So that's also a pattern, okay. Each number of this set has a pattern, so it means it is a countably infinite number, okay. So these rational numbers, as we can see, also has two major types here. The first one is what we first mentioned, the integer numbers, Okay, the integer numbers which also appears in some of the set like -2 here. Okay, we see -1 here. Those are integers. Okay, one, then we see 2. So if we express this further, we'll see some of the integers that are embedded there. Okay, so this number is divided into two. Number one is the integer numbers as we have shown. Then number two is the non-integer numbers. So the integer numbers we have discussed that earlier. Okay, but on the non-integer numbers, we can also divide this into three, or this has been divided into three by the LS mathematician. And these numbers are number one, uh, the number with a finite binary. Okay, the number with finite binary. Okay, are numbers whose denominator are usually the power of two. For example, 1 over 2, okay, is a finite binary, or another name for that finite binary is okay, don't forget we are talking about examples of this number which are non-integer. Okay, so we say the finite binary is also called a dyadic form of number, dyadic of finite binary. Okay, any number whose denominator is a multiple of 2, like 1 over 2, 1 over 4, 1 over 8. Okay, 16 in the denominator, not necessarily one of the denominator, but any number with multiple of 2, or the denominator 2, 4, 8, 16, 32, 64, and what have you. Okay, this is one type of integer numbers. Okay, the second one is the finite decimal numbers. Okay, let me see if I can have one like this number 3 over 4. No, this one is one of the dyadic. Okay, let me pick a number 3 over 5. Okay, 3 over 5 is as a finite decimal, because 3 over 5 is a 0.6. Okay, 6, and that terminates. Okay, so finite decimal or terminating decimal. Okay, though we described this earlier, we also, show some of the types of the non-integers that we have here. And lastly, the other types that we have here is uh, the non-integers with repeating decimals. Okay, and we can see many of them here, especially this 1 over 3 is one of them, because 1 over 3 is 0.333333. Okay, that 3 is like that till it occurs so infinitely. Okay, so 2 over 3 also has the same features, because it is 0.6666 like that too. Okay, and that is called the repeating decimals. Okay, so these are types of the number that we have here. Okay, so now to give a more let us describe this in summary, so that one can have a better understanding of what we are seeing here. In summary here, what we have just seen on this table is that the rational numbers, the rational numbers is divided into two first. Okay, that is the integer. Okay, I will use short form here in order to save space. Then non-integer. Okay, we have seen this earlier in our previous class, so I don't want to bother ourselves much on it. Okay, this one also has some that we have looked into before, but we haven't looked at it. We haven't looked at it before. Okay, so what we have said there is that under the non-integer, as seen on the table, we have some numbers that are uh, finite decimal, or terminating decimal. Terminating decimal. Okay, terminating decimals. Okay, we also see that we have some numbers that are repeating decimals. Okay, I think we choose the case 2 over 3. which is 0.666, and this continues like that. Okay. Another example is 1 over 3, which is 0.3333. Okay, we can see them many under this part. And then I think we choose a number at the right time. Under here, we can choose a number. Okay, though I didn't show some of the numbers, but example of this is 3 over 5. Okay, which is 0.6. Okay, so finite, because this will know we go no more. Okay, so and the last one we have said here is the one with finite binary. Okay, this is the number we say it has a multiple of 2 in the denominator. Okay, so you can see then there are those numbers are many there. Finite binary. Okay, like the number 1 over 2. You can talk of a number 3 over 4. You can talk of a number 7 over 16. Okay, as you can see, this has a multiple of 2. Those numbers have multiple of 2, 2, 4, 8, 16, 32, and what have you. Okay, those numbers are very useful in the computer science. Okay, the mix of them in computer science, because they are the one that give a finite binary under the binary number systems. Okay, and also this number is also useful in music. Okay, for those who are based in that aspect knows this very well. Okay, and we make use of this number too in for measurement, and some of the earliest mathematics education, the make use of this number very well. Okay, for some study. Okay, but uh, the study here will not cover that now. Okay, so these are the types of number that are embedded in the rational numbers. Okay, again, the rational numbers is basically divided into two: the integers and the non-integers. Okay, the integers, we have talked about them in our previous class. Okay, so we are just seeing this for the first time in this class. Okay, and we have said this is also divided into 3. That is the final decimal, the terminating decimals. We also say that any number has a finite decimal, but the denominator here is not multiple of 2. That is finite decimal number. Okay, again, the repeating type like this. Okay, let me add more so that we can. Okay, like here again we can see a number 1 over um, 1 over 6. Yes, if you look at this 6, is not a multiple of 2. Okay, though 2 is one of the factor, but it's not a multiple of 2. Okay, so 1 over 6. Okay, this one too give us any number give us a finite decimal there. Okay, you can think of a number 1 over 3 too, which is 0.333 like that. Okay, and the binary is the finite binary. Okay, so these are some of the numbers we. Okay, so the other names for this, let's make these summers. Okay, because we may see it in another context. Okay, they call this, either you call it finite binary or dic dialogue. Okay, okay, so these are number whose multiples of whose denominator has multiple of 2. Okay, so now let us see some of the other things here. You will recall that if you have a number over a number like this that will call rationals, we say this number, integer numbers are inside it. Okay, those integer can only be gotten if the denominator is 1. Okay, so that if we say that this a is 2, 2 divided by 1 is 2. Okay, any number a divided by 1 is a. Okay, these are the number that we can call the integer numbers. Okay, so we refer to these types of number under these rational numbers as embedded integers. Okay, okay, or embedded fractions. So that's how uh, we do it. So now let us look at some of the properties of this number, because it is the properties of a number system that make us to differentiate or between one another, and is the property that tells us which how bigger a number is. Okay, in terms of the properties. So let's see some of the properties of these numbers. So properties of Q. Okay, Q, set of rational numbers. Number one. Okay, so let me be using the notation Q1, okay, to mean this is coming from the uh, the rational numbers. Okay, so number one, any number we assume in this set, okay, is a rational number. Okay, so now for the sake of I'll be using the number P and Q as elements in this set. Okay, so if you choose a number Q to be here, okay, so the number P, okay, has this form, okay, and the number Q has this form. Okay, so we'll call this N1 to show that this is a natural number, okay, from P, and we'll call this the N2 to show that this is also a natural number from the set of point Q. Okay, so now I want to check for the addition properties. I want to say that and there is a closure property under addition. Okay, so if we let these two numbers to be an element here, then P plus Q is also, okay, so I will repeat this here anyway. P plus Q is also a rational number. What are we saying here? That is, if P, as we have posted earlier, is this, and Q is this. Okay, here you will see that this AB are integers, and N1, N2 are natural numbers. Okay, so what we are saying here is that if you add these two numbers together, this simply means this. Okay, so the same is N1, N2, and this gives AN2 plus BN1. Okay, so what we are saying is that this sum, okay, is inside, or this term is inside the, it's also a rational number, as you can see. Okay, and this also valid for subtraction. Okay, that is, if you let P, Q an element of Q, then subtraction also, that is P minus Q, is also a rational number. Okay, I can perform the same task as this, that P minus Q is A minus N1 minus B minus N2. Okay, and this is similarly N1, N2, and this is a AN2 minus BN1. Okay, what we are saying in essence is that this is also a rational number. Okay, so we can also find that of the multiplication. Okay, this is for addition, this is for subtraction, the next one is multiplication. Okay, so let's do that. Can use this. Okay, so we'll call this Q3. that if P and Q are element of the set of rational numbers, then P dot Q, okay, is also rational. Okay, and let's see that P dot Q will give a n1 multiplied by b n2, and this is ab n1 and 2. Okay, so what we are seeing is that the answer here is also a rational number. Okay, and for division, we will see that in any of this case, this denominator does not give 0. Okay, there is no way we get 0 in the denominator. Okay, because these two numbers are natural numbers. Okay, so again, for the division, okay, for the division, if you let p q to be an element here, then this division also holds it. Okay, and this also means that pq is a this, and this is a bn2, and this is nothing but an2 divided by bn2 bn1, sorry, bn1. Okay, this is also a rational number. Okay, so the next one is the equality. Okay, so let's see. Okay, we'll call that 5. So if P and these are members of rational numbers with P equal Q, okay, so then what it means is that you know that P equal Q implies that AN1 equals BN2, and this also implies by cross multiplication, this implies AN2 equal to BN1. Okay, so if two rational numbers are equal, okay, so this happens. Okay, so I think we are used to this in some of our elementary math. Also, the 6 that we can recall here is that if P, this is about the ordering of the rational numbers. Okay, if this happens and the P is less than Q, then we can say that uh, PQ, P less than Q. Okay, this also means this. Okay, and this also means by cross multiplication, this is also an2 less than bn1. Okay, so this is about the ordering uh, under the rational numbers. Okay, so next we can talk about the inverse under this. So when we say inverse, okay, it suffices for us to pick a number and then look for the additive inverse of this and the multiplicative inverse of it. Okay, so let's quickly do this under 7. Okay, for any P in Q, okay, for the case of the additive inverse, okay, there exists uh, negative P in Q, okay, so that so that p plus negative p is 0. Okay, so we can also do similarly for the additive identity. We can also for this, as you can see, where 0 here will be the identity. Okay, identity under rational number is usually fixed. Okay, that must be noted. Okay, so for the multiplicative inverse, and what we are saying in essence here is that if you since p is rational, what we are saying here is that this negative p is actually this number negative a over n1. Okay, just as it. Okay, and we have the result. Okay, so the okay, let's call this Q7A. That is for the additive inverse. So for the multiplicative inverse, we call that Q7B. Okay, Q7A for the additive inverse, then Q7B for the multiplicative. So for any P in Q, there exists P inverse in Q. Okay, of course, with P not equal to 0, okay, such that P dot P inverse, okay, of in terms of the commutativity, okay, if we reverse this, okay, this is actually 1. Okay, under the multiplicative inverse, okay, we say the identity is also 1 here. Okay, and the 1 is also fixed under the rational numbers. Okay, so these are some of the properties. Other forms are the exponential. Okay, let's say Q8 now. Q8. Okay, let's do this quickly. So for P and Q, and K is a positive integer. So if K is a positive integer, then P raised to power K is also a rational number. Okay, where this power is a positive integer. However, if this K is 0, of course, this follow the normal law, which is P raised to power 0 is 1. Okay, 1 is also an element here. Okay, so one can think of terms like this, and these are some of the properties here. Though well, the ones we can capture for now. Okay, so if you want to extend this further, we didn't talk about the identity. I've said identity was okay, so that's another form of example, both for the additive and the multiplicative identity. Okay, so that is that on the properties of the rational numbers. So there are some things we need to look at uh, under these rational numbers. The fact that these rational numbers, okay, is valid under addition, under the operation addition and multiplication. Okay, so this makes this rational number a field. Okay, because it has satisfied some of the properties of field. Okay, under the addition. Okay, under the addition, we have defined the closure property under addition. So since it is closed under addition, it means commutativity is there. Okay, and we have also said that identity also holds and inverse also holds under addition. The same thing can be repeated for the multiplication. Under multiplication, we have shown that it is closed. Since it is closed, it will be commutative too. Okay, identity also holds and the inverse also holds there too. Okay, so this Q, called the set of rational numbers, is a field. Okay, so let's make it formal. let's just make a statement here about this before we uh, round up on these numbers. So we want to note this based on the above properties that we are mentioned. Okay, so the set Q of four rational numbers together with the operations addition and multiplication as shown above is a field. Okay, so it's a field. So we have to note this. Okay, so as explained under addition, we have said closure property use, commutativity use, identity use, and inverse use. The same thing for multiplication. So, and these things we have mentioned and attributes of the field axioms. Okay, so it is also worthy to know that this field that we are talking about here, okay, this set Q, okay, of rationals, okay, is a prime field, okay, is a prime field. And why do we say that? This is the first types of set of numbers that satisfy the field axioms. You will recall that the natural number we have discussed earlier does not satisfy the field axiom with some reason that we have given in our previous class. The integer number also does not. The first set of numbers that does so is the set of integer numbers. So this Q, okay, does not have a subset which satisfy the field axiom, and this is why we call it a prime field. Okay, this is because this Q has no subfield other than itself. Okay, and what we need to note also from this set of integer numbers is that this set of integer number is also dense in itself. Okay, let's say let's say this more formally. Okay, the set Q is a densely ordered set. What do you mean by this? That is, if P and Q are elements of Q with P less than Q, then there exists another number. Okay, this time let's say R. There exists a number R in Q. Okay, such that P is less than R, less than Q. Okay, so it means any two rational number we pick, no matter how close they are, in between the two rational numbers, there is another rational numbers. And what this means is that this set Q is also dense in itself. Okay, so that's why we say this is a densely ordered set. Okay, so these are some of the basic properties or features of the rational numbers that we talk about for now. Okay, so in our next class, we'll look at another types of number, which is somewhat the opposite of the rational numbers. So, but before then, okay, I say bye for now.